Yes. Yep, so hello everyone. Welcome to the TEED talk, actually the last TEED talk of the semester, and we have Xinlun Cheng from Virginia, and please.
All right. So hi everyone. I'm Xinlun Cheng. I'm a fourth-year graduate student from University of Virginia, and I'm currently in a joint program between the astronomy department and also the School of Data Science. And today I'm very honored to be invited to Caltech to give a talk, and the topic of my talk is more data, no problem, into the age of industrial scale astronomy. Okay. So firstly, a brief introduction about myself. I have a background in physics and also astronomy. And I've also got my Master of Science in Data Science in 2022. I have been awarded 2 fellowships during my time at UVA, and my research experience are focused on galactic astronomy and also physics-aware deep learning. The theme of this talk will be focused on industrial scale astronomy requires new and more sophisticated data analysis techniques. And I will explore the theme using 3 projects that I have some experience in. The first one is exploring the galactic warps or asymmetries in the kinematics of the galactic disk. I will use this to mention one of the progress we made on a well-known phenomenon with new and more precise data from Gaia. The second project I will be talking about is galactic disk velocity field and problems with the KZ problem, where I will mention why new and more data classical treatments need some kind of corrections to them and are no longer useful. And lastly, it will be more into the machine learning side. It will be searching for White Dwarf, M-Dwarf binaries using deep learning, where I will talk about data mining with pre-training fine-tuning paradigm when the label training set is limited. So let us begin. So first, a brief introduction. What is galactic warp? Galactic warp is the bending of a galactic disk. You can see in the image over there. Do you have a laser pointer?
We have the manual one.
Okay, it works.
Yeah.
You can see in the image here, the orange line roughly traces out the shape of the midplane of this particular galaxy. One thing you will immediately notice that, contrary to common belief where the galaxy should be a thin, flat pancake-like stuff, it's actually warp. It's not in a straight plane. So this is known as the galactic warp. It was found in the majority of spiral galaxies, and it was first detected in the Milky Way in around 2000. It was believed to be either long-lived or repeatedly generated. However, we are not sure of it. The origin of the warp within the Milky Way is still under debate. And even the geometry, the shape, what it looks like. Does it look like this or something else? For the Milky Way warp, we are still uncertain of it. Well, that's partially because we are inside the Milky Way, and it's pretty hard to get to know what you are currently inside of. So, in this work was actually done in 2020, so we only have access to kinematics from Gaia data release 2, chemistry from apogee, distance from star force. I will introduce what star force is later, and then we'll move on to explore asymmetries in the outer part of our galactic disk. So our data set consists of 2 samples. The first one is purely Gaia, entirely Gaia. It's from DR2 proper motion plus star force distance and also the radial velocity from Gaia. We have some magnitude cards for signal-to-noise ratio regions and also to filter out some of the most brightest stars. Those are most likely to be biased or have some problems within Gaia. And we also remove stars with suspect photometries or unreliable radial velocity measurements because they don't have enough widgets. The second one is a cross-match between Gaia and apogee, where we use the proper motion from Gaia, however, the star force distance, the radial velocity, and also the chemistry from apogee. We then move on to chemically select thin and thick disk. Thick disk is above. I didn't label it in this plot. So finally, what is star-Horse distance? Star-Horse distance is a Bayesian estimation of stellar parameters, distances, and extinctions from a combination of many surveys. For example, for the Gaia one, they just take the photometric and parallax information from Gaia and a number of other surveys. But ARC-G one is slightly different because ARC-G has spectra, so they can pin down what kind of star it is very precisely. And that would actually give us a very good estimation of the star parameters and as well as the distance. So what did we see? Well, there are some kind of structure in the vertical velocity. The mean stellar vertical velocity increases with angular momentum, like shown here. This was previously observed in less detail and attributed to the Galactic warp. However, we made some new discoveries. The first thing is there's a peak and around here and around 6 kilometers per second. And then it decreases afterwards. So this is the first time that we have discovered a decline in vertical velocity for the Milky Way. Well, the other thing we found that there are a number of these ripples. Some of them are relatively well aligned with where the spiral arm or the galactic bar rotation should be. However, some of them does not correlate to anything. If we look at the ARC-G thin disk population, you can still see the same kind of global trend of increase and then decrease, although the decrease only have 1 or 2 data points, since ARC-G has much less stars. However, you don't see this kind of structure in thick disk. Another phenomenon that was previously discovered for the Milky Way warp is what is known as the Lopsided Warp. So it was first discovered through StarCom, where they measured the up and the downside of the warp and find that they are not symmetric. So they give it the name lopsided. We decided it might be better to characterize this with stellar kinematics. We find that for example, in the plot here, the peak velocity, that's also where the warp is strongest, where the warp is strongest should be. It's around 170 degrees in galactocentric azimuthal angle. So what is galactocentric azimuthal angle? Here is a figure to illustrate that. The sun is at 180, the galactic center is over here. And our peak velocity is around this. So you can see it's not directly at the sun, but it's pretty close. And then we move on to see what the rate of change in the vertical velocity is, and see if it is symmetric with respect to the 170-degree peak. We have data roughly around 120 all the way to 240 degrees. And as you can see here, the rate of increase is pretty slow, but the decrease is very sharp. So that means, through star kinematics, we are capable of proving that the Milky Way warp itself indeed is lopsided. So what can we get from all those observations? Well, we see a decrease in the velocity, but does it tell us anything physically? Does it tell anything? How can we characterize how the Milky Way warp looks like? Well, we built an analytical model based on James' equation and included a few terms that are generally ignored. We find that the stellar warp begins at around 9 kiloparsec with a precision period at around 450 megayears. To put that into context, that's around half of the speed of galactic rotation at the solar position. And then we animated our model with Blender. As you can see, the precision rate of the warp is really not very quickly when compared to the pattern speed of the bar and the spiral arm. And lastly, we would like to examine how different stellar populations of different age, how the warp affects them. so-called dynamically evolving warp. Well, we get our stellar age from centers and that's they got their age through Bayesian isochron fitting by combining radial velocity and stellar parameters from a large number of surveys. We found out that the warp parameters are actually dependent on age. The warp amplitude, as you can see here, decreases when the stellar population age increases. However, the precision rate, which is not shown here, but it does not vary. So this can be explained away by warp created through a gravitational mechanism within the past 3 gigayears. So, in conclusion, we are the first to discover a decrease in vertical velocity in the outer part of the galaxy. We found clearly repose in both vertical and radial velocity structure. We are capable of better characterizing the lopesidedness of the galactic warp. We are able to interpret the warp with a simple James equation analytical model. The warp begins at around 9 kiloparsec, and the precision period is around 450 megayears. The warp does show some kind of evolution with time. With the younger population, the stronger response. And it is possibly caused by an external gravitationally induced phenomenon within the last 3 gigayears. So our work was selected for press release during WS237, and we kind of made a big news for our department and also university at that time, because our press release got picked up by all kinds of media around the globe. So let's move on to the next product, where I will talk about galactic disk velocity field and problem with the KZ problem. I'm sure a number of you guys already know what KZ problem is, but just as a reminder, KZ stands for vertical force. So the vertical force problem refers to measuring galactic potential with vertical motion of disk stars. Essentially, it's doing a two-step process. The first one is solve a combination of Poisson and James equation to get the vertical force. The second step is to find a mass model that fits the calculated vertical force. Astronomers have begun to look at this particular problem in the 20s and 30s, but they have tiny samples, poor distances, and kinematics measurements. At that time, astronomers had no idea what thick disk or dark matter is, so they cannot include them in their model, and they get wildly discrepant results. In fact, if you compare all of these results to the ones that are most commonly accepted today, those are all wrong. However, in the 80s and 90s, astronomers are capable of doing a much better job because we have bigger samples and better data. And we also know that dark matter exists, so we could include them in the model. And if you're familiar with the KZ problem or galactic astronomy as a whole, you will know that this shape actually looks quite like standard halo model, the one that is mostly commonly accepted today. So in more detail, here's the traditional analytical approach. We restrict ourselves to the galactic pole because it is much easier to filter out the stars that we don't need that are closer to midplane. Why? I will mention that later. And then we assume time dependence and also a flat circular velocity curve. And then we could get this equation as seen over here. So all of the previous studies, they used stars with vertical height of greater than 1 kiloparsec. That's where the thick disk population dominates. And this helps to avoid complications of overlapping population with different kinematics and densities. So they could basically adopt the scale height and scale length of the thick disk without having to distinguish thick disk, thin disk, and halo stars. And then they do the measurement. They calculate vertical velocity dispersion and look how it behaves with the vertical height. Well, they usually use a linear function because, as you can see here, there's a global trend of increase. And the linear function is the most simplistic function that could also capture this trend. And then they move on, plug everything into that equation, get your surface density or the vertical force. these two numbers are related by a factor of constant as seen in the Poisson equation. And then they compare it with the model predictions. And if somehow the model and the calculated KZ does not agree with each other, then they play with either the scale height, this number, or increase, decrease the dark matter density. So obviously there are a number of limitations. For example, the larger scale height, the larger vertical height does not necessarily mean just thick disk stars, but it could be hard to discriminate thin disk, thick disk, and halo stars without chemical information. So how about outside solar radius? Most of the research, they are limited to within the solar radius, within the solar neighborhood. How about using thin disk stars? There are more of them. They're closer and easier to measure, should give us better results. So in this work, once again, we use a combination of Gaia and AlpG. However, we now have data release 3, DR3. So we will have huge samples covering large parts of the galaxy that includes outside the solar circle and also closer and further away from the main plane. We then perform a chemical selection of thin and thick disk stars. This would allow us to separate thin and thick disk near the main plane and also extend the range of coverage in both vertical and also radial direction. Equipped with this larger database, we can perform a test to see how the traditional analytical method works. So once again, our data is pretty similar to the previous one. However, it's more updated using DR3 proportion. This time we don't have Star Horse distance since DR3 was just released, so we take the Gaia distance. However, it is also a combination of parallax and photometric distance estimation. We then perform some quality cuts. After we use DR17 radial velocity plus Gaia distance. And once again, some quality cuts, and then chemically separate the thick disk, the thin disk, and halo stars. So what do we find? First, let's start with velocity dispersion profile. What does it look like? Well, it looks like a crudely drawn bird, right? Here are the wings. So people in our group start to calling it the bird's plot. In the inner disk, as shown here, the velocity dispersion increases with z, regardless of population. However, there are also some small-scale fluctuations in velocity dispersion. Well, within two particular peltocentric bands, we saw a huge and sudden decrease in velocity dispersion in the r direction. And it only happens within a few hundred parsecs. And this is likely due to the influence of the galactic bar. So what do we find near the sun? Nothing surprising. The thin disk has smaller dispersion than the thick disk because it is dominated by younger stars. The dispersion continues to increase with vertical height, with the rate of increase faster for thin disk than the thick disk. And from the velocity dispersion alone, we can realize that it is actually a mixture of all three populations. However, unlike AlpG, Gaia does not provide any chemical information, so there is no way to discriminate from each other. In the outer disk, unfortunately, we are quickly running out of thick disk stars since the thick disk has a much shorter scale length. We also saw a smaller dispersion that reflects the less mass density in the outer part of the disk, and also a smaller rate of dispersion increase. So before we move on to comparing our result with model, let me give you guys a brief introduction on what standard halo model is. Standard halo model is the most commonly accepted dark matter halo model of the Milky Way. It follows an NFW profile, so a Navarro Franken-White profile. It is the common shape of a dark matter halo as seen in many numerical simulations and has been observationally confirmed by gravitational lensing of galaxy clusters and many other observational campaigns. It is a good description of high-mass dark matter halo, but it has problems on the smaller mass scales. Fortunately, the Milky Way it's pretty massive galaxy. So we could use an FW profile. First, a sanity check. If we are going to look at how our results look at in the other radii, if we want to push the boundaries, we need to first determine that we are doing things correctly. So we perform basically the exact test with thick disk at solar radius and large scale height. Our results are in good agreement with previous studies. We pick two of them, particularly here as showcase. And it is also in good agreement with standard halo model, just as all the previous studies have established. However, moving into other radii and using thin disk, things break. We have three major problems on our hand. First, there's a mismatch between the thin disk measurement result and thick disk. It is very prominent in the inner part of the galaxy. We also find that our calculated surface mass density is not zero as z equals 0, although by definition it should be. And generally, there are excess mass near the midplane when compared to standard halo model. And in the outer disk, at large scale height, the numbers we calculated are not consistent with standard halo model. This could possibly be due to disk flaring. So, all of the previous assumptions, the traditional methods, including the one that we are trying to investigate here, they made a pretty large number of assumptions. How do all the assumptions hold up? And we would like to take a closer look at that. So the most common one is the density profile. They use an exponential disk. It's not an empirical model. It's supported by previous Starcom studies. But as you can see, it's not smooth at the midplane. So this will create some problems, since if you look at the equation itself, it requires a derivative of the density profile with z. Well, others have also tried secant squared. It's an analytical model that describes a self-gravitating disk. It is guaranteed smooth across all vertical values. However, there are major differences between secant squared and exponential when the z is pretty small. In fact, within the range that we have data that we are interested in, they are not necessarily close to each other, although asymptotically, their behavior is the same. It also has a problem that it approaches exponential too slowly. So this would lead to a worse result at large vertical height. That means if you switch to a more physical model, you would actually not be able to reproduce what previous people has done before. How about velocity dispersion profile? Well, it's linear, as we have used here. It's the simplistic model that could also capture the trend. But once again, it's not smooth at midplane. Spline is about a much better alternative. It's data-driven, so you could avoid assuming some kind of model, since more likely than not, there's no model, no analytical model that could describe the velocity dispersion of the entire galaxy. However, sometimes you get sections of decreasing velocity dispersion in the trend, like around here. This is actually not the most egregious sample. We've got even worse ones. This would be a serious violation of physics, since the physics requires whenever there's non-zero mass, the velocity dispersion should always increase with z. How about our model? Would we be comparing it to the wrong thing? Well, there are some theoretical work that suggests a non-FW halo. It could explain away the excess mass near the midplane. However, the previous two assumptions we just talked about, they have the most major impact to our calculated value near the midplane. So that means our surface density calculation is actually less reliable at midplane. How about non-equilibrium and time dependence of the galaxy? Well, we know for a fact that our galaxy is not in equilibrium, and the older population is usually less perturbed than the younger population when there is net impact. Perhaps this could explain away the mismatch between thin and thick disk. However, our exploration also shows that the effect should be small. So, in the end, we applied the traditional analytical approach to a hugely enlarged database. We can match previous studies and also the model itself at solar circle focus on thick disk stars. However, we found problems in previously ignored ranges and samples. And there are majorly 3 of them. We tried to explore various ways to fix this problem, but we could not get a very satisfactory answer. So this prompts us to say that it looks like to be the end of traditional analytical approach to the Milky Way problem. Well, the galaxy looks a lot more complex with larger data sets, and observed detailed stellar kinematics cannot be accurately described by simple relations anymore. And now for something completely different. So the last project I'm going to talk about is using deep learning to search for White Dwarf, M Dwarf using Gaia stellar spectra. This is currently working in progress. So a brief introduction about why White Dwarf, M Dwarf binaries are interesting. Well, White Dwarf main sequence binaries, they are the progenitors of many transits. For example, type 1a supernova or gravitational wave sources. And the most common of them are White Dwarf, M dwarfs. Since there are more M dwarfs within the main sequence stars. They are estimated around 1 billion systems. However, we only found around 3,000. That's a very small number. So how did astronomers find this kind of binary system before? Well, it's through template fitting and comparing the chi-square. Here's a spectra. This is actually a very outlier sample. The White Dwarf here is pretty strong. Most of the case, the flux contribution of the White Dwarf is basically you cannot just tell them apart by now. And it requires template fitting. You first fit an M dwarf and find the best fit M dwarf template, record its chi-square. And then you use a combination of White Dwarf and M dwarf. And then you compare the newly fitted chi-square to the ones using M dwarf alone. And if the combined template gives you a smaller one, well, then you would say, well, it's probably a White Dwarf plus an M dwarf in this case. However, this would require astronomers to go through thousands of combinations of M dwarf and White dwarf. Well, there are spectral subtypes for M dwarfs, and also metallicity would affect what the spectral template looks like. And also M dwarf and also White dwarf spans a huge temperature range, so you need a lot of combinations in order to get your measurements accurately, and it gets computationally intensive very quickly and becomes basically intractable if you want to run on a large data set. Well, how large data set we want to run on? It's Gaia 3. There are 200 million low resolution spectra. Even if we just restrict ourselves to M dwarf-like spectra through color magnitude diagram cuts, there are still 8 million of them. And if we cross-match this with the previously known White dwarf main sequence callouts, we'll get around 600 of them. So I only have 600 and want to use machine learning. Let's take a look at what previous studies have done. They have run some kind of random forest model on a simulated gas spectrum, and it's capable of achieving 60 to 80% overall accuracy. And there are 3 major limitations within their study. The first one is synthetic training set. Well, it is not guaranteed that your synthetic training set would look basically indistinguishable from observed ones. And in many cases, you could discriminate them rather easily. The Gaia spectra, because how it is encoded, it has a lot of small wiggles that we don't see in their synthetic training set. However, this research was also done before Gaia DR3 was even released, so they only had access to synthetic training sample. Second limitation is their accuracy. 80% is not bad, but I believe we could do better. And 60%, well, it's only a little bit better than coin toss. And what if we want to make more contribution to data mining projects using Gaia spectra? Can we transfer whatever they have into other problems? The answer is no. A random forest algorithm is basically specific to that problem you are trying to solve. All right, so in this work, we use real Gaia data set, and we propose a much more complex machine learning model. We're trying to build our architecture around a more easily transferable for other data mining projects with Gaia spectrum. And we finally settled down using pre-training fine-tuning paradigm. And this paradigm was solely seen in astronomy. Before we move on, let's give you a brief introduction of what deep learning is. So deep learning is basically neural networks, training, testing, designing neural networks. So what are neural networks? Neural network is a bunch of neurons connected together, often in layers. And neurons are weighted sum of its input and decide what value to output based on its sum, using what is known as an activation function. Within the many types of neurons we could have, one of them is particularly interesting. It's known as a convolutional layer. Convolution layer basically convolves the input from here with a trainable filter. In this case, the filter itself is 3 by 3. You take a weighted sum of these pixels and you output it over here. This can be very useful in hierarchically summarizing your input information. And basically, it is required in dealing with structured data, like, for example, an image, or in our case, a spectrum. So a convolutional neural network is a neural network with many convolutional layers, like the one shown here. There are only 2 convolutions in this particular network, but in a real, very deep neural network, you could get upwards of 10 or even more than 20 convolutional layers. In fact, a neural network, especially a convolutional neural network, can be viewed as a feature engineering segment plus a classifier segment. So the feature engineering segment takes whatever your input is, through convolution and pooling, eventually projects it onto a high-dimensional vector representation, like here. And then this representation is fed into a classifier or a regression. And that part is usually, for example, a multi-layer perceptron. In this particular case, the input is an image. They are projected to a 16-dimension vector, and then it is taken for classifier. And the classifier is capable of telling, for example, whether it's dog or cat, or in this case, it should return there are both in this image. So, as you can see, that network is it's pretty complex. It has a large number of parameters. You could easily get like 1 million or even 10 million parameters, trainable parameters within a neural network. So this would require us to have a large labeled training set in order to show the neural network basically, here's a picture of a cat, here's a picture of a dog, here's another cat, here's another dog, repeated millions of times. But as we said before, we only have around 600 training samples. So that's a problem. You don't even have the number of samples to match the number of parameters you have in a network. So can we do anything about it? Yes, through what is known as a contrastive learning. Contrastive learning is a semi-supervised learning method. The intuition of contrastive learning is based on what I've just introduced before, that neural networks are essentially functions that project your input into a high-dimensional vector representation. We want different input to have different vector representations. So this would preserve as much input information as possible. For example, here, a picture of a dog and a picture of a chair. we don't want to just feed the entire picture into it. We want it to summarize it. However, at the same time, keep as much information, for example, where the dog ears are, where the eyes are, and what does the entire image looks like within the high dimensional vector representation. Well, if we only have this one constraint, your network will overfit. It will find some ways to project every single input into a different vector. And we don't want that, because that means your network will get incredibly confused when your input have noise, and also the representation is essentially useless because your input image itself are different when your input image is different. So we also want similar inputs, for example, pictures of cats or pictures of dogs, to have similar vector representation. So it will be robust to noise and unimportant details. So how do we do that? Well, through a data augmentation. Data augmentation is basically a fancy way of saying adding noise, changing your input in such a way that your network is capable of, you want your network to ignore those changes. So in this case, it's basically cutting the image into small pieces, changing its color, making it black and white. You want these representations, like shown here, the representations that are gathered from the data augmented input of the same image to look like each other, to attract each other. However, you want different ones. For example, a chair, and a dog. These representations should repel each other. They should look as differently as possible. So one very good thing about this contrastive learning is that through the entire training process, we don't tell the network what this or this actually is. So no labels are necessary. That means it could learn the general features within a dataset on its own. And then when it comes to finally do the classification problem, you do what is a fine-tuning step, where you freeze all the convolutional layers. These layers, the weight within them no longer changes. Then you train a multi-layer perceptron on your limited training set. So the final classifier are then trained on the limited label training set. So if instead of images, what will happen if the input is a spectrum? Well, here's a Gaia spectrum. We input it, and through data augmentation, we acquire two spectra. They are much more noisy than the ones we have before. And now we feed it into a one-dimensional convolutional neural network. We get some hidden representations, also through a multi-layer perceptron to get the final high-dimensional vector representation. And just as we said before, we want these two to be pretty close to each other, since they are essentially the representation of the same spectrum. So what are our preliminary results? We're capable of getting 91% accuracy in our holdout testing set on fun team. So holdout basically means this testing set, the network has never seen it before. So we have a training, a validation, and a test, a holdout test. All the other, like, for example, how to avoid overfitting are all focused on using training and validation set. So the network has never seen testing set before. So we also run it on the roughly 8 million AMDOFs and pick out a few high probability candidates. For example, here's the negative candidates. Well, the black line is the best fit AMDOF template we have. It looks pretty similar. For this particular positive candidate, you can see that you got some excess flux in the plural wavelet set, and it is very likely that there is a white dwarf here. Here's another one. You can see here, the template itself is still a pretty good fit. However, sometimes the positive candidate is not very, you cannot just say it like, yes, this is a positive candidate because they have some kind of excess flux. Yes, there is a small amount of them, but it's also pretty noisy. However, if you do the fitting, the black line, the White Dwarf template, is not the best fit. So some other researchers I've done, well, focusing on astronomy, I've also done some kinematical analysis of substructure in the southern periphery of the large magnetic clouds. We discovered some kinematically interesting and distinct population at the southern periphery of LMC, and they are likely due to the interaction between LMC and SMC. And in terms of data science, I'm working with a bunch of people from the physics department on a joint project in convolutional neural network for large-scale dynamical modeling of itinerant magnets. And for those of you that has been to the pizza lunch today, that this is the particular one that I introduced about. And yeah, since some of you are interested in what the Hamiltonian looks like, it's here. And as you can see, the network is capable of modeling the force pretty accurately. So it could form this kind of skirming vortex and also keep it stable. And lastly, I would like to give thanks to my advisor, Steve Majewski, the postdoc that has been in our group and very beneficial to all of our progresses, Bohan Anguialu, our collaborators within the Department of Computer Science at University of Notre Dame on the Gaia Spectra project, Xinlun Cheng, UV Research Computing, Gaia and UpG mission, and also Jefferson Scholars Foundation. Thank you. Any questions?
Yeah, I have a question on the Gaia spectra.
Yeah.
So in order to get the spectra that you showed, there's this reconstruction process, well, polynomial.
Yes.
You know, this processing to get to a spectrum you can do science with. Given your methods, is that necessary, or can you just operate on whatever it is that comes out raw? That you actually need to make a spectrum to do what you're doing?
That is a very good question. In fact, you can, like, if we just build a neural network that is known as a, how do I say it? Yes, using only fully connected layers. Like, since we are building a convolutional neural network, it requires convolution to make sense, right? A convolution in spectra makes sense because you are just doing a weighted sum of some neighboring data points. You are basically averaging over the spectrum in a way. However, if you use, if I remember correctly, they are using Hermite polynomial. If you use the weight of the Hermite polynomial alone and you run a convolution, it doesn't make any sense because the basis are Hermite functions, and you are actually smoothing a bunch of functions using their weight of combinations. So that would create a lot of problems for us. And also, one major advantage of convolutional neural networks, other than using like fully connected layers, is that since we are using only a trainable filter, like the filter itself could only be 5 or 3, they only have 5 or 3 parameters in them. However, if we want to build like a fully connected layer, that would mean your input may be 50 of those Hermite polynomial coefficients. Then you will connect it to your next layer. So that means you could have hundreds of parameters like within one layer. And the major problem we are having is basically a limited training set. So we don't want that many parameters to train. And lastly, just as a data scientist would say, if it works, then yeah, it is the correct approach.
Any other questions? Any questions from audience online?
Okay.
Well, yeah, if not, let's thank Xinlun again.